Finance involves a lot of uncertainty, and we use the language of probability to model that uncertainty. The common distributions of finance occur in many ways, sometimes directly, and more often as the building blocks for more complicated processes. So let's take a look at a couple of examples of how we compute expectations from distributions, how we can solve some interesting problems from some simple ones. And let's start thinking ahead already as we review probability to thinking about how we're going to use these basic tools of probability to describe processes that evolve over time, where we need to think about uncertainty over multiple horizons in the future, and where information may arrive gradually from one point to another and get incorporated in our description. So our starting example, let's just think of a random variable x, a binomial random variable, where I have probability p, that we sometimes call success, of getting a 1, probability q, which is just shorthand for 1 minus p, of getting a 0. The typical question we ask, and that we saw in lecture, is what's the probability of observing a fixed number, say k, successes out of a total number n of trials? So to do that, there are two common things that we do. First, we ask for a given sequence, what would be its probability? Well, if there are k successes and there are n minus k failures, then the probability has to be p to the k, q to the n minus k, because the events are independent, their probabilities multiply. And then there are a lot of different ways of doing that. How many? Well, we've got a sequence of n events. The ones could be placed at any orders between them. The number is n choose k, probabilistically, and this is the familiar binomial distribution. Sometimes written k of n with parameter p, the probability for success. Now, suppose we ask a different question. Suppose we ask how long it would take us to observe success. That is, we don't know what n is in advance. We'd like n to be the outcome. So n is our random variable, or we might call it t to think about a waiting time. So let's call t the waiting time. And that's how long we would need to wait for our first success. So what might happen? Well, we could have it happen on the first event, right? So we could have at t equals 1, we get a success, and that could happen with probability p. Could happen on our second trial. T equals 2, that is, we could fail at first, have a failure, and then a success, and that would be probability q times p. Third trial, if it happened at t equals 3, we would have fail, fail, succeed. That would be q squared p. And in general, we can see that for t equals n, we're going to have probability q to the n minus 1 p. That is, we have a string of n minus 1 failures followed by a success. And this is the geometric distribution. So we have that the probability that the waiting time is equal to some particular n is given by q to the n minus 1 p, or we can write that, of course, as 1 minus p to the n minus 1 times p. So how long should we expect to wait on average? Let's compute. When in doubt, compute. So the expected time, the expectation of our waiting time t, is going to be the probability weighted average of the waiting time. So we have a formula for that, so we can write this as the sum from n equals 0 to infinity of n times q to the n minus 1 p. Now, if we look at this, we notice that this combination here looks familiar, doesn't it? It's the derivative of q to the n. So we'll use a trick. What we're going to do is we're going to write it as a derivative, and then because q is positive and less than 1, the sums are convergent. and we'll interchange the order of differentiation and summation, which will give us something that will be a nice quick answer and something that generalizes for more complex cases. So let's see how that goes, taking it step by step. This is equal to, I'll pull the p out in front, times the summation of d by dq of q to the n, which I'll write as p d by dq times the sum of q to the n. And the term in parentheses right here is a geometric sum. So we can do that sum. This is just p times 1 over 1 minus q, and its derivative gives us 1 over 1 minus q squared. Now we remember that p plus q equals 1, so this is p times 1 over p squared. Therefore, we find that the expectation of t is equal to 1 over p. So this should make some amount of sense. First of all, we see that as p gets small, the expected waiting time gets large. If we have a 1 over 6 chance of throwing a 7 with a pair of dice, we wait on average 6 turns till we get that. If we're looking for a set of pair of 2 aces and playing poker, then we'll have to wait on average 221 turns. Now, it's important to note that in both these cases, they satisfy the Markov property, which says that there's no memory of what happened before. That is, if we just got a pair of aces, our expected waiting time for another pair of aces is 221. But if we've been waiting 220 hands, we still have an expected waiting time of 221. Regardless of what came before, the future expectations depend only on the present state variables for where we are now, not on how we got there. And this notion of Markov processes will be important for characterizing different kinds of time evolution and for the way in which information gets incorporated into interesting financial variables. So when it comes to games of chance, certainly we know that in a fair game that the next outcome is independent of the ones that came before, that each one should be independent. Let's now extend and ask what would be the variance of the waiting time. So for the variance, let's remember that the variance of the waiting time, or for any random variable, is the expectation, let's put it this way, of the variable minus its mean value, which here I'll just simplify the notation. Instead of e of t within the expectation, I'll just call t bar, quantity squared. Now we have the general property for all expectations that the variance is the expectation of the square minus the square of the expectation. Let's just review that. This is expectation, and I'm going to expand out the quadratic. T squared minus 2 t bar t plus t bar squared. Remember that t bar, the expectation of t, is just a number, whereas t is a random variable. Now, applying linearity, we have that the expectation of the sum is the sum of the expectations, and the expectation of a scalar times an expectation, we just bring the scalar out front, plus t bar squared. Now we notice that in this second term right here that we have t bar times t bar. That is, this combines to be minus 2 t bar times t bar, which gives us minus 2 t bar squared plus t bar squared. Minus 2 plus 1 is minus 1. So we have that this is equal to, as advertised, the expectation of the square minus the square of the expectation. So how do we apply that to our Bernoulli trial case? Well, we'd like to find the second moment. T bar we've already computed. It's 1 over p. So t bar squared is going to be 1 over p squared. So what we'd like to do for our Bernoulli case is compute the second moment. So we'd like to compute expectation of t squared, and that's the second moment. So this is going to be the sum from n equals 0 to infinity, this time of n squared, times the probability that t equals n, which is the same as we saw before. Now you notice we're not quite in as good shape as we were before because I have n squared instead of n, and this quantity here is not just the derivative of q to the n. But we can come close. We can still use a derivative trick in a slightly different formula. And what we'll do is we'll notice that every time when we took a derivative once, we brought down a power of n. If I want repeated derivatives, if I just keep taking repeated derivatives, I'd end up with n factorial, which isn't what I want. So if I take a derivative but multiply back by q, then I will have what I want. So let's take a look. So specifically, let's look at the more general problem of computing, say, the moment t to the power r. And that I can write as, let me take out this p here, and let me take out 1 over q out front. So let me write this as p divided by q times the sum from n equals 0 to infinity of what would be n to the r q to the n. And I'm going to write that in the following way. Q d by dq with this operator raised to the rth power times q to the n. So if r is equal to 1, I take q d by dq gives me an n times q to the n minus 1, multiply by q, and I'm left with n with a single power of n in front. If I do that repeatedly, twice, 3 times, r times, each time I act with the operator q d by dq, I'll bring down in front a power of n. So this is going to be equal to, this is going to be the same thing as p over q times the sum of n to the r q to the n. So obviously we can apply this in the special case where n equals 2. But we want to do one more thing, which is to do our derivative trick. So where we interchange the order of the derivative and the summation. So let's put this in the form p over q, q d by dq. Let's take this operator to the rth power times 1 over 1 minus q. So here's your chance. Take these formulas that we have here, take a moment right now to go ahead and compute what is the variance of t. So compute the expectation of t squared and subtract the expectation of t quantity squared and express the results in terms of our original probability value, p. Okay, hit pause now if you haven't got it yet and you want a little more time to work it out. But the value that we have is we have now that the variance of t for the waiting time for a success in a single series of Bernoulli trials is going to be the expectation of t squared minus the expectation of t quantity squared, and this is equal to 1 minus p over p squared. So we have a general formula that we could extend to computing higher moments, and we can apply this to other settings where perhaps a Bernoulli process like this might be part of a more complex sequence of conditional probabilities. Let's take a look together at the code for simulating the scaling of the binomial distribution in R. You can install RStudio. It's freely available for PCs, for Macs, for Linux. And when you install it and you open it up, you should see something like this. So there are 4 panes. On the left-hand side, on the lower left, is the console area, which is where we'll type commands interactively. On the upper part is where you'll see source files, and this is the code that is in the slides. It was during recitation. On the lower right is where plots will show up, where help information is given, where you can see a list of installed packages that are part of your particular installation. And on the upper right is where you can see the variables you've created. So let's take a look through the code one step at a time, run it together. You should do this along with me or after watching this short video, and go in and tweak the code, tweak the parameters, run it yourself. You should get your hands on with the code, try it out. There's nothing special about R necessarily, but it's a great language to learn. It's very practical. If you don't know it, now's a great chance to learn. And in the finance industry, you will find that while people may have all kinds of different opinions about what the pros and cons are of different computational environments, usually on the job you don't get to choose. Or even if you're in charge, you'll eventually have to interface with a counterparty who's going to have another choice. So it's always good to know new languages, to keep the ideas separate from the particular code implementations and ready to pick new things up and try them out, particularly when you've got a problem to try as you do here. So let's do this together. Anyways, let's go through our demonstration. So the first thing, which is a bit R specific, is I'm going to define a list of values that I want to try. So nList is going to be the name of my variable. The left assignment arrow, the less than dash, you can use an equal. It works fine. That's a symbolic thing, and it's conventional in R. And then the C operator concatenates. It's a list operator. It creates things. So my list consists, instead of going every step 1, 2, 3, 4, 5 up through 1,000, I just picked some convenient samples. In RStudio, I can take this. I certainly could take this line, and I can type it in the lower part and run it. And if I type nList, I'll get my values out. And you notice that in my list of my environment variables, it showed up here in the upper right. However, if we're working with code, and you've got more than just a couple lines interactively, you may find it helpful, as I do, to open a new window for an R script as a scratchpad, or in more structured examples, an R notebook. Keep them up here. And then if you want to run something that's highlighted up here, you can highlight one or more lines of code, click on Run, and it will run your selection. So let's take a look for those values of n. I'm going to define my probability to be 10%, and we can change that in a moment. And then I've got a for loop. So the for loop is going to take n to run through all the values in the list, and then the contents of the for loop are enclosed in brackets. So white space is not important. Unlike Python, indentation is just for the convenience of the user. It's not read by the language. So everything between those two brackets is repeated within the for loop. I'm going to let k go from 0 to n is going to be a list of all the integers. If you want to see what that looks like, if you just type 0 to 5, it'll give you the value 0 to 5, or 0 to 12, it'll give you 0 to 12. So what we're doing is for each value of n, so for n trials, we're going to let k go from 0 successes up through all of them being successes. You could think of the number of heads in n flips of a biased coin. And then we're going to compute the probability for each one from the binomial distribution. Now this is a built-in function in R, and if you want to take a look at what it is for any function, you can type d binom to get the description, or over here in the help panel, you can just type in what you want. So if you want to see for any other distribution, for the beta distribution or so on, you can get its details. So this is all the details you need for the binomial distribution, along with some examples and some references. So we're going to use the binomial distribution. The conventions are the same ones that we used. F will be our distribution function. K is the number of successes. N is the total number of trials, P is the probability of success. Then having done that, we just need to draw some pictures. So we'll use the bar plot command, and you can read about that here. I'm going to use, for now, the basic base package R commands. There's other popular packages like ggplot, which have much more sophisticated and interesting aesthetic options, but we'll just get our base results for right now. So the bar plot is going to plot the values of f. It's going to plot the names label, is going to give the labels that correspond to each bar, and then xlab and ylab are the labels on the plot for the x-axis and the y-axis labels. Main is the title of the graph, and this paste command concatenates a bunch of string variables and numbers together so that we can get numerical values on our plots. And then readline is just a pause command. It waits for input at the keyboard so that we can build the graph successively as I showed you. So let's take this whole thing. I'm going to select all of this text. I can include the comment, and I'm going to hit run. And now, down at the bottom, it's waiting for me to hit a key. So if I want to expand this graph so it fills up the whole thing, these little icons over here will expand it. If I want to see both of those at the same time, I can do it, and I can resize the window between them. For right now, let's make this big. Let me resize this to give us a little more room. So what we can see here is two plots. I've done one trial. There's 10% probability of success. Therefore, the chance of 0 successes is 90%. The chance of 1 success is 10%. No surprise there. Now I'm going to click Put Focus in the lower right and hit Return, and it draws the next. So this is incremented by 1. So now we're looking at n equals 2. There are 2 trials. I could have 0, 1, or 2 successes. The probabilities are 81%, 0.9 squared, down to 1% for the chance of getting 2 successes. If we keep going, these are the different values, and as I hit return each time, you see the graph drawn in the way that we did in class. Okay, so I can go all the way to the end. Now, if you want, you can go in and you can pick a different number. You could pick that this could be, let's say, 30%, and rerun the whole thing to your heart's content. And if we rerun this now, we have that's for 1, 2, 5, 10, 20, 50, 100. And you see the features that we saw in class, which are we started with an asymmetric distribution, and we're getting something which is actually fairly symmetric about the mean. It's also looking pretty Gaussian, isn't it? We'll see in a moment how we can rescale the variables to get the true universality behavior that we expect from the central limit theorem. Keep in mind that whenever we're running a numerical simulation, though, whenever we think about either using a random number generator to get Gaussian variables or looking at the relationship between binomials, binomial tree models, and Gaussian distributions, the binomial distribution with a finite number of steps cannot go from -infinity to infinity. It can't go negative at all. And in this case, the maximum value that we could have would be 100. Given that the probability of being in the tails becomes very, very small very quickly, we wouldn't see that on the graph. But remember, in finance, we often care about rare events. And getting the probability of rare events wrong on a picture like this might not seem that big a deal. It's a rounding error in the number of pixels in the corners. But in finance, the consequences are often proportional to the distance away from the mean. So we frequently run into situations where we have events of interest that have very low probability but very high consequence. Multiplying the two together gives us an economically significant number. So we can't just look crudely at pictures on a graph like this. Okay, so if we keep going, that's 1,000. Now, let's take a look at our scaling variable. Remember what the basic idea was. We want to have the scaling variable under which the distribution looks stable. It doesn't keep shifting around and moving to the side. And there's one thing that we might want to keep in mind, which is that we always have, for any random variable x, that where its moments exist, if we have x and we can compute its expectation, Let's give that a name. Let's call it mu, let's say, or x bar. And we can compute its variance, and let's assume that that exists also. And let's give it a name. Let's call it sigma squared. That if mu and sigma are any numbers for our distribution, we know that for our binomial distribution, the mean is n times p. We know that the variance is n times p times q. But for any values of mu and sigma, we can take any variable x where mu and sigma exist and define a standardized variable. Then we do it in a very trivial construction. Let's call it define z to be x minus the mean of x. Guess what? The mean of that variable by construction is 0. What about its variance? Well, its variance is going to be sigma squared. So let's just divide this by sigma. And if this is a definition, this variable z is always going to have 0 mean and unit variance. So let's go back to our example, and now let's look at our code for rescaling the sequence. And here we're going to look at the same set of values, but now what we're going to do is after we define k, we're going to define z to be a rescaled variable. That is, we're going to take k, we're going to subtract its mean, and we're going to divide by the square root of the variance. And then we're going to plot the results. Okay, I'm going to cut off so we're going to cut off our graph at values of plus or minus 5, just so that we can see everything that we're doing. And now if we take our list, let's run this again. Same command. So this time z is going to be our scaled variable. F is going to be the binomial distribution, and let's take a look at the plots. So I've highlighted the text here. I'm going to hit run. Oops, let's make sure that we get that right. We need to highlight the entire thing, including the top definitions of those variables. So let's do that and hit run, and you could run these one at a time or type them in. So here's in terms of our scaling variable. So here we've got for n equals 1, and I've set p back to 0.1. And now for n equals 2, n equals 5, n equals 10, n equals 20. And now you can see that within the same picture, our graph is staying centered. And as I get to larger and larger values, we see that we've reached the central value to be in the middle of the graph, to be our rescaled variable equal to centered around 0, around the mean value in terms of our rescaled variable. And our shape is looking quite Gaussian. Try it out yourself, change the numbers, and play with the code.